Um, Great. So, hello, everyone. It's a bit of an odd experience for me because obviously I can't see any of you, but I'm going to have to assume that you're there and listening to me. So thank you for joining me today. My name is Yossi Synett. I'm head of AI and co-founder at StuffThatWorks. I'm going to tell you a little bit about what StuffThatWorks is in a second. Yeah, let's just get going, I guess. So StuffThatWorks is a platform that we've built to help people with chronic medical conditions to research their condition and figure out what works through crowdsourcing. But I want to start a little bit before that and talk a little bit about the problem that we're trying to solve, which starts with the fact that there are roughly 10,000 chronic medical conditions that people are dealing with. 6.5 billion people in the world are affected by them, and many of them have hundreds of potential treatment options. So of course, it doesn't take much math to figure out that it's impossible to compare all of these treatments' effectiveness through clinical trials, and certainly to get to a sense of kind of what's going to work for whom. In fact, there's really no single large-scale knowledge base about the experience of people with chronic medical conditions to this day. And it's clear that the people who are dealing with these conditions are not satisfied because they are out there on the internet looking for solutions. 10% of daily internet searches are connected to health and medical issues. Healthline is one of the largest kind of knowledge sites for health issues, has around 350 million visits a month, and there are more than or around 500,000 groups on Facebook connected to health. In fact, it's Facebook's largest single category in terms of groups. And yet, what you find is that there's really so much information, but people are unable to do anything with it. I don't know if anyone's been on a Facebook group and had that experience of coming into the group and or seeing someone come into a group and ask a question that has been asked 100 times before. How did your kid deal when you switch them from one reflux medication to another? But it's impossible. These groups are not really searchable in any meaningful way, and so people can't really benefit from other people's experience. So we figured that there was a way to solve this problem that no one had tried yet, involving crowdsourcing and AI. And it's really not a huge surprise that Yael, our founder and CEO, came to this idea, because her experience was with a company who you might have heard of called Waze, that saw a problem, the problem of people trying to navigate and get around traffic, and realized that that was a problem that might be able to be solved through crowdsourcing. So today we have a platform where people can join. You might have noticed on the first page, but so far up to almost 550 medical conditions, and people can actually come onto the platform and request new conditions and open them. And when someone joins our platform, they actually fill in a relatively in-depth survey where they share their experience in a structured way with their condition. So, general info about themselves, experiences with their condition, what symptoms they have, what triggers it, things like that. And most importantly, treatments that they've tried, whether they've worked or not, and whether they've been detrimental, etc. In addition, StuffThatWorks platform is building out to be able to support other sources of data, like geographical data, data from wearables, and ultimately connecting with medical records. So we started out, we really kind of launched a year and a half ago, but we started bringing people onto the platform a little earlier than that. And in that time, it's just grown and grown to the point where today we have around 1 million contributors across 550 conditions who have contributed up to date almost 60 million data points. And that means 1.6 million reports of treatments, 1.8 million reports of treatments, of symptoms, lots of data on what makes their condition worse and what other conditions they are experiencing. And we've done our work comparing a lot of the data that we've collected with consensus documents and guidelines, and indeed we're getting a pretty good picture of these medical conditions. Indeed, we've recently seen our first peer-reviewed paper published on a condition called plantar fasciitis. So we had a good sense when we got started what we wanted to do with this data. And indeed, if you come onto our platform, then you'll kind of see this timeline, which every community being the community of people dealing with a condition, has at the top, where we show that as we grow, we're able to deliver, greater insights. So at 50, we can offer general kind of descriptive insights about a condition. At 100, we start to share insights about what treatments people have tried. At 500, we offer our first look into treatment effectiveness, where we kind of take the whole community as one homogeneous group and rank treatments for what would work for the average person. And then at 2000, and this is actually something that we're releasing very, very soon, we offer effectiveness for subgroups, where we actually produce a treatment ranking that varies according to the people within the group and their symptoms and comorbidities and age and sex and gender and anything else that might impact what treatments are going to work for them. And then, our ultimate goal is to be able to offer people a sense of, personalized, not as part of a subgroup, but me as Yossi, what is going to be the best treatment for me. But as often happens when you collect a lot of data, you find that there are other really interesting things that you can do with it as well. Or as I like to say, we then accidentally created a map. So this whole thing started with a question, which was, since we have all of this data that spans so many different medical conditions, would we be able to do something with that in maybe the diagnostic space? After all, we have people who are coming onto our platform, they're reporting their symptoms and their, what makes their condition worse and what other conditions they have and age and sex and gender and all of those other things that I keep on mentioning. And we also know what condition they've been diagnosed with. So theoretically, as an AI guy, it's only natural that we think, well, wait a minute, we might be able to do something kind of diagnostic with that. And indeed, Yael, our CEO, came to me and asked me one day that question: is that something that would be possible? So we figured we'd give it a try. The thing is that the people who fill in our platform, the people who when people fill in a survey on our platform, a lot of the data that they fill in is actually free text. And the problem with a free text is that either you have to wait for it to kind of go through some kind of process of human labeling, or you have to try and use natural language processing. So we decided that for this model, we wanted to go straight down the natural language processing route. And amazing work has been done in the last decade, even more so in the last 5 years in the area of natural language processing, such that today, if I have a task that I need to do which involves language, whether it's sentiment analysis or even question answering, all kinds of different things like that, then actually probably someone has already solved a similar problem. And not just that, but there are what's called pre-trained models that can be used that actually are able to, that have been trained on a whole bunch of text and are kind of already able to understand text. And so we thought, well, what if we could take some of those pre-trained models and through a process called transfer learning, incorporate them into this diagnostic model that we wanted to build. So that's kind of how we started. And we built this kind of architecture where on the one hand, we have the free text responses on things like symptoms and aggravating factors, comorbidities, and treatments that people have tried. And on the other hand, we have some other features which are kind of more classic in a machine learning sense, numeric features like age of onset, categorical features like sex, and ordinal features like quality of life and people's body type or BMI. And so what we do is we actually we built this neural network, as I said, involving these pre-trained encoders that were already trained to deal with text, and we put all of that together and run and end up with a prediction from the neural network for the probability that someone has each one of the, say, 550 conditions in our database. A couple of I don't know, a couple of little points for the machine learning enthusiasts in the audience. So one of the things that we did here is that we wanted to basically create a what's called a shared embedding space. And maybe I should start with an embedding is a way of kind of representing something categorical or non-numeric in a kind of numeric way. In natural language processing, every word is represented by what's called an embedding, which is basically a vector of numbers which describes that word. And what you end up with is that when you have two similar words, then those two vectors are going to be very similar to one another. So we wanted to create that kind of embedding space, but for our users. And what we wanted to do was we wanted to put everything in the same embedding space. So the conditions and the users and the encoded symptoms and the encoded aggravating factors and even these other categorical features, they all live in this kind of same embedding space. And we use certain tricks to achieve that, things like residual gradients and other things. The other thing is we actually train two versions of the model simultaneously. One is what we call a condition fit. It's not meant to be used diagnostically. It's more used by us internally to measure how well matched someone is to the condition that they're a part of. And that model uses all of the data here that I've described on the screen. And then we have another model which is, again, more diagnostic in terms of its goal, and that only uses the features that are in black here. So specifically, it doesn't look at your comorbidities and it doesn't look at the treatments you've tried, because that might be too leading in terms of what condition you're actually dealing with. So a little bit further into embeddings, I'm actually going to skip because I just talked about it, and I'm going to talk a little bit about training the model. So as I mentioned, we have two variations in the model, and then we can measure the model performance. What we do is we as is common in machine learning, we kind of split our data into training data and testing data or validation data, such that we can test the model on data which it hasn't seen. And what we see is that when we just input the diagnostic features, we're already reaching an accuracy of 76% over, hundreds of conditions. And when we add those community fit features, then the accuracy increases to 83%. The meaning of the top 3 accuracy is that it actually 90% of the time with the diagnostic features, the correct condition will be in the top 3, and 94% of the time with the diagnostic and community fit, which is pretty cool considering we've really just trained a model to look at text and a few other things, and it's able to kind of reach these to reach these high degrees of accuracy. I will say that not having 100% accuracy is, in our case, definitely a feature as opposed to a bug. That doesn't mean that the right accuracy is necessarily 76%, but since we know that a certain amount of people are misdiagnosed, it's very interesting to actually see that our model doesn't reach 100% accuracy, and then look at which examples it misclassifies. And indeed, a lot of those examples are people who might fit better to another condition potentially. And then that opens the question, is this model actually telling us something about misdiagnosis? So then moving on, how do we end up creating this idea of a map? Well, the thing about, as I mentioned, in order to kind of do this prediction, every user ultimately becomes represented in our model by an embedding, by a series of numbers. Actually, right now it's 512 numbers that represent a user. Okay, so you could think of that as each user could be represented by a point in 512 dimensions. But of course, since we can't see 512 dimensions, we can't visualize that full space. But what we can do is use a method called dimensionality reduction in order to essentially squash that whole space down to 2 dimensions, and then what we get is this map that you're seeing here. The approach that we use, by the way, for that dimensionality reduction is called Tisney, and what it does is it tries to make sure that 2 points that are close together in the original space will be close together in the 2-dimensional space, which is exactly what we were looking for. So each point on this map actually represents a real user report, and actually the algorithm that creates the map doesn't directly see what condition the user has. The coloring is something that we apply afterwards. And so obviously you see that, as you'd expect, people with the same condition cluster together, because this embedding is supposed to represent the user in such a way that it could be used to predict what condition they have. But not just that, you start to see how we call them continents emerge of conditions which are similar to one another. So for instance, this area of mental health conditions, or this area of rheumatic conditions, or women's health, and then you also see that the points within the conditions aren't just kind of spread out in kind of a circular or uniform way, but actually there's a kind of structure within the condition communities, which might be indicative of certain kind of subtypes and things like that. And then finally, going back to the point I mentioned earlier, you can see that someone with in many cases, you see the examples of kind of miscoloration. So, within the big cloud of PCOS, there are a few points that are actually colored as endometriosis. And again, this might be the model essentially telling us that these are people who are, if not misdiagnosed, then at the very least, the information that they gave us is actually a better fit with another condition than the one that they've come with. So one cool thing that we can do with the map is also use it to show how other features kind of vary across the range of chronic conditions. So we can kind of color it any which way we like. So for instance, see how sex at birth varies across the different conditions, or which conditions report certain symptoms in a higher value, how age varies. And if you look closely, you can also see how those points kind of cluster together, but taking, for instance, the age, you see gradients occurring both within the conditions as well as across the conditions, which again shows how the structure within the conditions could be turned into kind of explainable subgroups for research purposes, for instance. And then going back to kind of where we started this, one application for this might be potentially a diagnosis. So, for instance, we can take a set of reported information, like the ones that we use to build the model: sex at birth, age of onset, BMI, quality of life, symptoms, and aggravating factors. And then the model is able to make a prediction. So here you see that this person with this set of criteria, the model predicts with an 89% probability that it's type 2 diabetes. And then additionally, other kinds of diabetes are also possibilities, type 1 being pretty marginal considering the late age of onset. Another way that we think about representing this kind of this flow for potentially undiagnosed users is, rather than to give them these probabilities, which might be a little bit too definite, to actually kind of show them where they land on the map. Who are they similar to? And here you can see that they're quite similar to the people with type 2 diabetes. So time's gone by since those visualizations that I've made, and today actually we're gearing up to release the map as a tool on our platform, and there's a bunch of different things that people are going to be able to use it for. Where it's going to be searchable in terms of people being able to type in a condition and land in that place on the map. If you're already a contributor on our platform, then you'll be able to zoom in on your condition and navigate around, looking at the people who are similar to you, for instance, and see how and kind of why they're similar to you. And we see that additional applications kind of growing in the future. And so going back to how I started this thing and kind of what I wanted to get across is the importance of when you're collecting a lot of data, you surely know what you plan to do with it, or hopefully you kind of know what you plan to do with it. But you should always keep an open mind for additional things that maybe didn't occur to you in the first place. We started out with this goal, and it's still very much our core goal, for people with these chronic medical conditions to be able to find treatments that work. And we're very much investing a lot of resource into that and a lot of AI into that problem. But today I wanted to talk about the kind of the serendipity piece, the things that you also discover along the way that you can do that actually maybe no one else can do because of the breadth of data that we have across all of these medical conditions. So that's it. I've got a little bit of time left, so I'll be glad to take any questions that we have. Right now, I've only got one question, or it wasn't really a question, it was a very nice comment. But if anyone else has any questions, then Okay, well, in that case, I will say thank you very much for your attention and your time, and feel free to look us up and get in contact if you have any questions that you want to ask privately. All the best, and thank you. Thank you for the people behind the Data Agility Day for this opportunity to talk. Okay.